very good morning to all of you. I hope you are rested during the weekend, tried out a few of the experiments, and we are now into the second and final week of the Radio Astronomy Winter School of 2021. This morning, we'll start off by getting an overview of the Milky Way, which is our own galaxy. And this first slide just illustrates to you that the Milky Way is something which has been familiar to ancient civilizations. This is an aboriginal drawing which is shown along with a visible region of the Milky Way from the southern hemisphere. And although northern hemisphere and many civilizations, the myths and legends are driven around the constellations, you'll find that among the Aboriginal Australians, there are a lot of stories about the dark spots, which we shall see in a short while, in the Milky Way. This particular region of the sky resembles an emu, and this is a photograph which has been put together by Barnaby Norris, who is son of a friend and collaborator astronomer from Australia, Ray Norris. And what it shows you is that this is when this part of the sky appears overhead sometime in August, and this is exactly a drawing which was done in Kurungai Chase National Park in northern Sydney, resembling this sort of emu in the sky. And this is the time when the emu lays its eggs. So this is a time for the indigenous population to also collect emu eggs, which was an important or a significant source of food as well. So we were tied to the heavens, or not only for our seasons, for our food habits, but also to find directions. And the Milky Way is something which is easily visible in dark skies, even from the northern hemisphere, but center of the Milky Way is more easily visible from the southern hemisphere. And that is where the center of our galaxy, the Sagittarius constellation. So this is a picture you must be familiar with, the beautiful arch and all the dark spots which you see when you look at the Milky Way in the optical region of the spectrum. And the dark patches are because of dust and gas which obscures starlight. This picture has been taken from the Parallel Observatory in Chile, and you can see the Magellanic Clouds over here. This is actually a smudged out picture of Venus because of exposure, and these are city lights from a nearby town, Antofagasta. And this sort of laser beam shows you where the center of the galaxy is, the Milky Way. So we'll have a brief glimpse of the history of our understanding of the Milky Way, and we'll look at what the modern science is telling us, more recent results as well. And some of the most phenomenal results in recent times have come from this telescope, which was launched, Gaia, in 2013, and is likely to operate till about 2025 or so. Now, initially, the Milky Way was thought to be the universe. That was all there is to it in our universe. And the Milky Way comes from the Latin word Via Lactea, which is the Milky Way. It is also referred to as the Silver River in Chinese and East Asian languages. In the Kalahari Desert, it was referred to as the backbone of the night. But ancient astronomers would not have been able to resolve stars. But in spite of that, atomist philosopher Democritus, who postulated the atom by breaking out a metal or whatever into smaller and smaller bits, speculated that a bright band may indeed consist of distant stars. But in those days, Aristotle held away. He was very well known, and he thought it was a contact between the celestial and the terrestrial spheres, as he put it. And this was what held sway till we came to almost the Middle Ages, or the Renaissance period, when Galileo with his telescope resolved stars in the Milky Way. And this is a bit from his book Sidereus Nuncius, which was published in 1610, showing the resolution of stars in the Milky Way into individual stars. Otherwise, it used to appear to the naked eye as just a diffuse patch of light. And as I said a little while earlier, that till the 20th century, actually, that this was thought to be the entire universe. And Al-Sufi, who is a very well-known Muslim scholar, obviously from the Sufi sort of lineage, as his name indicates, mentioned about a small clouds towards Andromeda in 964 in his book, which the English translation reads as Book of Fixed Stars in 964, Common Era. This was perhaps the first written record of a cloud, of a galaxy external to our own galaxy, although it was not known to be an external galaxy at that time. But of course, the Magellanic Clouds, as well as the Andromeda, Magellanic Clouds particularly, would have been known to the indigenous Australians since ancient times. And this is a beautiful, you can see the beautiful calligraphy and the beautiful sketching is wonderful. This is something which I just picked up from Wikipedia. Fast forwarding to the 18th century, that there were a lot of diffuse nebulae which Charles Messier catalogued. And Charles Messier was basically interested in identifying comets, but he didn't want to be confused by diffuse objects in the sky with the comets that he was looking for. So he made a catalog of all the diffuse objects in the sky, and they consist of a variety of objects. M1 is Taurus or the Crab Nebula, M31 the Andromeda Nebula, which you're all sort of heard many times, are near one of our near neighbors. And then we have M87 at the bottom, which is a giant elliptical galaxy in the center of the Virgo cluster of galaxies, and where the black hole has been imaged recently by the Event Horizon Telescope. But you'll see that his diffuse objects consist of a lot of nearby galaxies, both spiral galaxies with spiral arms and elliptical galaxies, which just look elliptical when projected onto the plane of the sky. He had fewer objects than 110, but some of the objects were added later by astronomers by looking through his notes. And this is one of the early catalogs and is known as the Messier's catalog. So when you see an M before an astronomical name, it refers to what Messier's catalog number in that object. Now the question arises whether these diffuse nebulae, before we could establish that they were external to a galaxy, whether they were part of our own universe, or whether they were external universes, whether the Milky Way was all there is to the universe or not. An English astronomer, Thomas Wright was a very versatile person. He was a mathematician, instrument maker, architect, garden designer, you name it. And he speculated that the Milky Way was a flat layer of stars. Our solar system is a part of the Milky Way. And he speculated that very faint nebulae, in all likelihood, may be external creation, bordering upon the known and too remote for even our telescopes to reach, which implies that the universe is much larger than imagined. And drawing upon the early speculation by Thomas Wright, his contemporary, the philosopher Immanuel Kant, referred to these faint nebulae as island universes. But the debate was not settled whether they were indeed island universes like our own, external to our galaxy, or whether they were within our galaxy. Then came actually precise scientific observations. William Herschel, the refugee musician from Hanover, who became the astronomer royal and built some of the most powerful telescopes of his time, he started counting stars and tried to determine the shape of the Milky Way from star counts, and found stars to be denser in some directions than the other. And he found the sun to be located somewhere near the center of the Milky Way. He looked at about 600 different locations, and he assumed the stars to be of similar luminosity, so that what you see, the observed flux or how bright it was, depended just on the distance. And he made a sketch, which you can see over here, which was reported in the Philosophical Transactions of the Royal Society of London in 1785. This was much before the Hertzsprung-Russell diagram, and much before we learned that stars have very different luminosities and different colors. As some of you who have seen the Hertzsprung-Russell diagram will recollect or will know even otherwise. Now, Kapteyn did a lot better than that. He collected photographic plates from different parts of the world and constructed a model of the Milky Way. And he too came to the conclusion the Milky Way was a flattened system, but his galaxy was larger than what Herschel had sort of speculated. And sun was offset from the center, but is still close to the center. Now I put a question, why does the sun appear towards the center in Herschel's and Kapteyn's universe? And that is largely because, as we shall see a little while later, that our galaxy consists of interstellar dust, which obscures the light from more distant stars. So it's like being in a forest where you see a lot of fog around it. So you can only see as far as the fog allows you to see. And if you can see only as far as the fog allows you to see, then what you will see are the objects within a certain radius. So their objects were reasonably, or the sun was reasonably close to the center of the galaxy. But that picture changed with Harlow Shapley trying to look at the distribution of globular clusters. Okay, and this actually, this was predated by Henrietta Leavitt, who looked at variable stars in the Magellanic Cloud, particularly in the Large Magellanic Cloud, and showed that there are certain kinds of variable stars called Sephid Variables, where the brighter stars take longer to vary on longer time scales. So once they varied on longer time scales and they were brighter, it required the distance measurement of Cephids in our own galaxy to establish that it was not just apparent brightness, but the luminosity of these Cephids were related to the period. Longer period Cephids had higher luminosity. So once you had that relationship and you could identify these stars, you could go and determine distances. So actually globular clusters are bright and big and can be seen to large distances. And once these distances were determined, Harlow Shapley, what he did was, he plotted the positions in the galactic coordinate system. And although this figure is a bit faint, what you can see over here, the shaded horizontal bar is the disk of our galaxy, and the filled circles are globular clusters above, and open circles are globular clusters below. And Shapley had actually, not correctly estimated the distance, because the effect of dust was to be established much later in 1930s, how widespread it was by Trumpler's observations of how the colors of the star change due to extinction or scattering of light by the interstellar medium in our own galaxy. But what he showed was that we are in no special location in the galaxy. These globular clusters were uniformly sort of spherically distributed roughly, but they were roughly distributed around a point which was about 8 kiloparsecs away. 1 parsec is about 3 light years. So 8,000 would be about 24,000 or 25,000 light years away. So that was the center of the galaxy. So we are in a very nondescript part of the galaxy. Not only got dethroned from being the center of the solar system, but we are also not in any special location in our galaxy, but about 25,000 light years away, about 8 kiloparsecs away. But whether these island universes were within our own galaxy or whether they were outside it, there was a very famous debate which took place on 26th of April 1920 between Harlow Shapley and Herbert Curtis. It was at the Natural Museum, and they tried to argue whether these spiral nebulae were within our galaxy or outside it. Shapley argued that they were within our galaxy, whereas Curtis went by what Kant and Thomas Wright had speculated, that they were outside our galaxy. And Shapley's also arguments were based on observations by Van Manen of a particular galaxy called the Pinwheel Galaxy, which Van Manen claimed he saw rotation of the galaxy. And Shapley argued that if he saw rotation in this galaxy and if it was much further away, then it would really have to be traveling at faster than the velocity of light, or extremely high velocities, which were untenable. We later realized that Van Manen observations were not quite correct. And today we know that the spiral nebulae were indeed island universes outside the Milky Way. But how did it get established? That really got established with the identification of Sephid variables in our nearby galaxy, M31, the Andromeda Nebula. And it was Edwin Hubble who identified Cephids in M31, looked at its period, estimated its luminosity, knows its observed flux, and so he could measure the distance or estimate the distance of Andromeda. And that put it at a distance of 770 kiloparsecs, far outside the size of the Milky Way. So Andromeda Galaxy, as many of you may know, is approaching us at about 300 kilometers per second, and it should collide with the Milky Way in about 4 to 5 billion years or so. So once this was established, that these island universes were indeed external galaxies. So we are not going to spend much time about external galaxies today, because the objective of today's discussion or presentation is to look at our own galaxy. And this was the dark patches which I pointed out to you right in the beginning, which Barnaby Norris had shown similarity or with the carvings, stone carvings of Aboriginal Australians. And these patterns are due to absorption by dust in the interstellar medium of the galaxy. Otherwise, the galaxy is without a telescope. You can see that when you look at the night sky, you'll see the stars separately. But when you look at the Milky Way, given the density of stars and you're seeing them all along a line of sight, they appear as diffuse clouds over here. And you can also see the large and the small Magellanic clouds over here. Now you can ask yourself also that, you know, that wavelength, the extinction is wavelength dependent. Longer wavelength radiation is affected less by extinction. And an everyday example which you see is that when the sun sets or rises, the longer wavelength red light comes through and the sun appears reddish, whereas during the day, the blue light is, you see the scattered blue light and the sky appears bluish, okay? Now, similarly, suppose I looked at the universe or looked at our galaxy at long wavelengths, will I be able to peer through the dust? And the answer is yes. And this is an infrared image of the galaxy where you don't see the dark regions in the galactic plane are not seen. Infrared regions, at near infrared, it'll be affected to a certain extent, but as you go to longer wavelengths, it'll be affected less and less. And similarly, if you were to look at a radio map of the galaxy, which we shall do in a short while, you're not going to see any dark spots because the long wavelength radio waves will come through unaffected by the dust. They, of course, do get affected by the plasma frequency, as several of my colleagues have pointed out earlier in the winter school. For example, the ionosphere cuts us off roughly at about 10 megahertz or so. Now, one can ask oneself that the Milky Way appears as a diffuse patch of light, okay, diffuse patch of light. And but what fraction of the volume is occupied by the stars? And what I'll try and show you today, normally I'd have asked you to sort of estimate it for me, but being a short class, I will 1 hour class, I will sort of show it to you just to give you an idea that although most of the mass of the visible matter is in stars, it occupies an extremely small volume. And to do that, I will just try to estimate for you what is the fraction of volume which is occupied by the stars. So let's take our own sun. So the sun is a radius of about 700,000 kilometers. And the nearest star, Proxima Centauri, is about 4 light years. I put it in kilometers over there, so that it's easy for me to take ratios of volumes. And if you do that, you'll get the fraction of volume occupied by the sun. So it's about 1 part, you can see few parts in about 10 to the power of 24. It's a very, very small fraction. To get a physical intuition about what this number means, you can take 100 kilometers. 100 kilometers, if you change it to millimeters, you'll get about 10 to the power of 8 millimeters. 10 to the power of 3 will come from meters. Then you have 100, 10 to the power of 5, then you'll get centimeters, 7, then you'll get millimeters 1. So if you enclose a volume of about 10 to the power of 8 millimeters with 100 kilometers, that's about 10 to the power of 24 millimeters cubed. So if you had a sort of biggish grain of sand or a small pebble, I mean, if you had one in Bombay, you take another 100 kilometers away, say Pune, as the crows fly somewhere in Pune, that is the kind of separation between the stars compared to the size of the star itself. Obviously, it will vary, but this gives you an idea about how sparsely the stars are actually populated in our own galaxy as well as other galaxies. Towards the center, obviously, it will be more tightly packed. Globular clusters are very tightly packed, but the general distance gives you a general feeling. So that if two galaxies were to collide, and they just consisted of stars, they could actually just go through one another with some perturbations, but not very severe effects. But we know that the medium between the stars is not empty. It is the interstellar medium that exists. Now, this is the kind of picture of our galaxy. If you were to look at it edge on. Now, reconstruction of this has been an interesting story in its own right. I'll give you just glimpses of it to whet your appetite, and you can read up much more. I will share this PDF file, and you can look at many of the references which I've given over there. Okay. Now it consists of a disk, okay, which you can see over here edgeways. We are here, and there's a bulge in the center. We will also look at a face-on view in a short while. And we looked at the globular clusters. Globular clusters are basically very dense condensations of stars. I'll show you one or two pictures in a short while. And these globular clusters are more or less spherically distributed. So, and then also in this halo where the globular clusters are, there are also old stars. There's stars in the halo as well. So the kind of stars which exist in the disk of the galaxy and those which exist in the halo of our galaxy, they are often distinguished by what are called population 1 stars and population 2 stars. Not very imaginative names, but simple names. Population 1 stars are young stars in the thin disk, and you can get them in open clusters. Open clusters and globular clusters I will mention in a short while again and elaborate on it. And population 2 stars are old stars. They are in the bulge and the halo and in globular clusters. And in the bulge, we find that they are generally the population 1 stars are metal rich. In astronomy, anything heavier than hydrogen and helium are referred to as metals, whereas the population 2 stars are metal poor. And in the bulge, you'll get metallicities, which are old, somewhat metal rich, not as metal rich in the disk, but not as metal poor as in the halo of our own galaxy. So just to recap what I've said in just a short while ago and show you a couple of pictures as well, that there were 2 types of stellar populations. And this was actually brought to the limelight by Walter Baade, who was looking at stars in the Andromeda Nebula, this nearby galaxy M32, Messier 32, and NGC 205. And he noticed they had 2 different colors. And he also noted over there that these 2 types of stellar populations were pointed out by Jan Wood way back in 1926, looking at stars in our own galaxy. So as I said, population 1 stars are metal rich. That means they have more of heavier metals than hydrogen and helium, found primarily in the disk and spiral arms of the galaxy. They orbit about the center of the galaxy. It consists of both young and old stars. I'll just finish this slide and you can ask your question. It consists of young stars in Orion, the sun, are examples, and metal poor are found in the bulge, halo, and disk. We'll look at the orbits a bit later again. They're random elliptical orbits. They're old stars formed early in the evolution, and typical ages, they're older. So what happens over here is that these are stars which have formed more recently. So they formed from interstellar material which has already been enriched with metals, and so they are metals, okay, metal rich. So we look at the orbits a bit more closely. This is a picture of a globular cluster. Open clusters are just loose associations of stars consisting of hundreds of thousands of stars, whereas globular clusters are dense, they're more or less spherical, and can consist of thousands of stars, tens of thousands of stars. Okay, Sanyukta, you had your hand up and somebody else also had his hand up.
Yes, please, I had the question about the globular cluster. You just mentioned the population density is a little more than this part. So is it because of the presence of the supermassive black hole at the center?
No. This is just, these are globular clusters are condensations of stars which seem to have formed very early in the evolution of the universe, of our galaxy. They are, as I said over here, about 13 billion years old. So they're a gas cloud, probably which collapsed to form these stars from the primeval material from which our galaxy may have initially collapsed. Supermassive black holes exist almost in all galaxies that we know of, but these globular clusters need not have a supermassive black hole at all. Okay, they're generally old stars and they're metal poor because they have formed from a primeval sort of cloud, where a lot of star formation has not taken place, whereas the population 1 objects are those from which stars have formed. Okay, the enriched material is from which population 1 stars are formed. Lakshmi Raja?
Yes, sir. Sir, you mentioned about the dark spots, which we can see in our galaxy. So, Can you just explain what are those actually meant? Like when we say dark spots, what do they show us?
Actually, suppose I had a light screen coming from it, and you had something which is blocking that light. Suppose I put up a screen or put up an object in front. So compared to the background light, it will cut off the light from the stars and you're going to see it as a darker region. just like any cold spot in the sun. That analogy is not quite correct. Okay, but anything which obscures the light will appear darker. So here what is happening is you have dust and gas in the interstellar medium, which is actually cutting off starlight from behind. So that is why it appears darker. All right.
Okay. So that's, I mean, true for only some parts, right? It doesn't obstruct the whole.
It depends. It depends. It is more in some parts than the other. So it depends on the structure of the galaxy. It depends on the distribution of dust. For example, when you read about elliptical galaxies, you'll realize that they have much less dust than spiral galaxies, very little dust at all. So there the obscuration will not be there. But sometimes you get dust rings around elliptical galaxies as well. But they generally have less dust than spiral galaxies. So you will not see the kind of complex patterns which you see usually, but there are exceptions, many exceptions. But wherever the dust is, you're going to see dark spots and cuts of light.
Yeah, okay.
Okay, Palak?
So what is halo?
Halo. Okay, any bright object, for example, this is our galaxy over here, and I said this is the bulge, okay, and this is the disk of the galaxy. So halo is the material which is around it, okay, around it. Okay, this is what is referred to as the halo. Okay.
Sir, how did we decide that this is the disk of the galaxy, like the plane of the galaxy and not like some other plane?
How do we decide that this is the plane of the galaxy? Okay,
So why are we like not taking the vertical plane or like some other angle?
Okay, how do I determine that the galaxy indeed has a plane? The galaxy indeed has a plane because I can look at the distribution of objects in our galaxy. How are they distributed? You can see straight away over there that if it is not in a plane, it is going to be spherically distributed, just like the globular clusters are. So by looking at the distribution of objects, like the stars, the gas, the neutral hydrogen, for example, which Subhashis talked about the other day, are distributed in the plane of the galaxy. By looking at the location of stars, pulsars, bright young stars, old stars, you can go and determine how they're distributed, and that is how derive the plane of the galaxy. The galaxy plane also has structure. So maybe have a look at, wait for that and see if you're still unclear, and then you can ask me again.
Okay, sir.
Okay. Sanyukta?
Yes, sir. I wanted to ask that, like, can we ever see the face on picture of the galaxy? Like, we can see the edge on because we lie on the disk, but will
So
we be...
suppose you're inside a forest. Can you say what the forest is looking like if it's full of fog?
No.
No. So you cannot. You have to determine from observations what our galaxy might be, edge on and face on. You cannot go outside our galaxy and have a look, right?
So we kind of predict, like using the current observation we can see from edge on. We try to.
So I would encourage you to wait for a little while and then ask your question again. Okay.
Okay.
Because I think you're asking questions which you'll get the answers to if you wait a little while. So Amrita, is it anything different you want to ask?
Somewhat similar, sir. My question was actually regarding the first slides where you mentioned William Herschel and Jacobus Capitan.
Yes.
So you said that they pinpointed the location of the sun in the drawings, but my question was, since the sun would be visible in the morning and the Milky Way would be visible during the night, how did they ever determine the position of the sun? Like, how could
Well,
they pinpoint
you don't make observations from the sun, right? You make observations from the earth. And the observations and the earth would be effectively the same as the sun, right? In terms of the distances that we're talking about.
Right, but my question was again same as Samyukta, as in...
You'll have to make optical observations only at night, right? You can't make observations during the daytime. So
how could we pinpoint our own position?
Well, the position of the earth would be the position of the sun, effectively. Won't it? That's just one AU when you're talking about parsecs and kiloparsecs over there. Yeah?
Yeah, that was my question, as in how did they pinpoint the position of Earth or the sun? How did they do that?
By the relative, these are relative locations, right? Relative locations. Suppose you look at, you're in a particular location, you imagine yourself on the surface of the earth, and you look at objects which are around you, and you look at where you're located relative to those objects, right?
Right.
For example, if you saw many persons in a field away from you compared to in the other direction, then you'll be able to say that you're on one side of that crowd compared to the other. On the other hand, if you're in the center, then you will find people and your friends are all uniformly located in a field, then you'll find yourself at the center, won't you?
Yeah.
Okay.
Thank you.
So can stars somehow migrate from the disk to the halo and vice versa?
I will come to that. Okay, I will come to that. So reserve some of your questions. Okay, reserve some of your questions. I'll come to that in a short while. All right. Now, just as we talked about the edge-on view of our galaxy, we can also try and determine the face-on view of our galaxy. And as I just mentioned, we cannot go outside our galaxy and determine what galaxy looks like, unlike external galaxies, but we can reconstruct it by looking at the distribution of objects. Okay. Now, initially, as I mentioned, that in the optical region of the electromagnetic spectrum, you cannot see very far, and that is because of obscuration by the dust and gas, which make up the space between the stars. Okay. But nevertheless, we have been able to reconstruct it by looking at very bright objects, such as very massive stars, which are extremely bright. Then we have been able to look at it in the infrared region of the spectrum, which goes far deeper. Then we have been able to reconstruct the map of our galaxy from neutral atomic hydrogen observations, to which we will see from the furthest reaches of our galaxy, as Subhashish pointed out to you during the experiment on H1 measurements. So from all the different kinds of observations that we have been able to reconstruct how the material may be distributed in our galaxy. So I have illustrated over here some of the main arms of our galaxy, of a spiral galaxy. For an external galaxy, you'll be able to see these arms quite clearly, particularly if that specific galaxy is in face-on. But on the other hand, we are inside it. So we have to reconstruct, it's like reconstructing a crime from all the little pieces of evidence that you can collect. And you can see the prominent arms marked over there: Scutus Centaurus arm, the Perseus arm, and these main arms are seen attached to a bar. These have the highest densities, largely of young stars, but both young and old stars. And the two minor arms, you can see the Norma arm and the Sagittarius arm, which are less distinct between the major arms. Here is the Norma arm. Okay, and then there is the outer arm as well. And there is a shorter 3 kiloparsec arm, as it is called, which is identified from radio observations. As I mentioned, radio observations can see much deeper. And the sun lies over here in what is called the, where's my cursor gone? Here, which is known as the Orion Spur. Sometimes it's called the Orion arm as well. And there's a weak outer arm as well. Now, these have been put together by looking at the distribution of stars, pulsars. Remember, Vishal Gajjar showed you an image of what the distribution of pulsars would be when a square kilometer array and the ASCAP, they all sort of make their surveys, and we have tens of thousands of pulsars. They were largely tracing the spiral arms. But right now, if you remember Vishal Gajjar's slide, that most of the pulsars were in the vicinity of the sun, and that is because we have not been able to see very far. But on the other hand, this is a constantly evolving picture. Okay, constantly evolving picture, because we need accurate measurements of distances. And one of the very well-known telescopes which has gone up is what is the Gaia telescope, the Global Astrometric Interferometer for Astrophysics. And they are trying to measure distances with astrometric accuracies at a micro-arc-second level. And there have been suggestions that the arm structures may be more complex and complicated with more accurate determination of distances. But this is an unfolding story, and understanding of spiral arms is itself extremely interesting, which will be egged on by new observations from Gaia as well as other telescopes. Now, just to summarize again, what I said over here is that this is the disk of our galaxy. This is a reconstruction, as I said. This is the bulge of the galaxy. Galactic center is over here. We are over here in the center. And this is an example of a globular cluster. And I just wanted to show this because I'm going to refer to the galactic coordinates, which Subhashish also did, that the galactic coordinate system is centered on the sun, okay, not on the center of a galaxy. Towards the center is longitude 0, and then it increases 90, 180, 270, 360. And when you look towards the north, it's the galactic north pole. And when you look towards the south, it's a galactic south pole. So this is the broad sort of structure of our galaxy. Okay, so major components: disk, bulge, the bar, stellar and gaseous halo of the galaxy. And this gives the scale in one slide. Okay, and again, I should mention there are no sharp boundaries, but you can draw, this is an illustration of it. We are over here about 28,000 light years away, 25,000 or so, and we are here, and this is the thickness, which also has a certain scale height. And there's a very famous song by this Monty Python, which is sort of surreal humor group from England, and you can listen to it. And some of you are good at singing, maybe even sing on it, but the numbers are reasonably good to describe our galaxy. Now, in addition to what I've shown you, there is a dark matter halo surrounding our galaxy. Okay, and that is something which we shall have a look at it in a short while. Okay, now, after a little while, I'll pause, but I just wanted to go ahead a little bit so that some of the questions which you are asking may be preempted by what I'm going to say. So a disk is approximately circular disk of stars which rotate about the center of the galaxy. Okay, I've given the luminosity and the mass of the disk which have been estimated. Extends to about 15 kiloparsec from the center of the galaxy. So roughly 30 kiloparsec in diameter. Don't pick up a fight with somebody who say it's bigger, because the density doesn't fall off sharply. It depends to what brightness you want to define it. Also, it depends on what is the component you're measuring. Neutral hydrogen may be is seen to further distances than the stellar light, and density falls off exponentially, both vertically as well as radially. So when you look at a disk, there is a thin disk with a vertical scale height of 300 parsec. These contain the young stars. They contain the dense components of the interstellar medium, the molecular clouds, which are the densest, coldest regions, as you will hear in a short while from my friend and colleague, Mr. Srianand. And this thin disk contains 95% of the stars in the disk. And the older stars, which are presumably puffed up from the thin disk, dynamically heated as well. And these are about a kiloparsec. So the disk also has structure, and these are all interesting areas of study as to how they formed, how they evolved. Then the bulge of the galaxy, which we talked about 8 kiloparsec from the center. This perhaps contains some of the original stellar population. Bulge is metal poor, but not as metal poor as the halo stars. And when we look at face-on galaxy, which I probably perhaps forgot to highlight, is that you see a bar as well in the center. Okay, and we'll briefly allude to how these structures may have formed without getting into too much of detail over there. So now halo, then there's a bar, there's a stellar halo of all metal stars, which are about 10 to the power of 9 solar masses or so, and most appear to be within about 30 kiloparsec from the galactic center. They could be debris from tidal disruption of dwarf galaxies. They're globular clusters. There may be stars which are formed while the galaxy itself was trying to form, which are left behind in the halo while gas clouds collapse to form the Milky Way. And there is also a hot gas, which one can pick up in X-ray region of the electromagnetic spectrum, which is extremely hot. And this is about 1,000,000 degrees Kelvin or more. And these are components. This is a component which is probably ejected by supernovae, massive stars when they explode. Heats up the gas to very high temperatures, as you have learned so far. Okay, I should say just a little bit more about the bar. Bars are due to dynamical effects. These are slight changes in potential which deviate the stars from their circular orbits, and they form sort of elliptical kind of orbits. They're temporary phenomena. They come and they go, and strong bars have the potential to actually drive gas inwards as well. Okay, I will just finish 2 more slides and then I will take another set of questions. Okay, and in addition to that, what we have is a dark matter halo. Okay, and dark matter halo we will see how we come to, because all our galaxies are buried in dark matter halos, are embedded in them. And when I said about halo stars being forming by the tidal debris of stars or of dwarf galaxies, which may be interacting with our galaxy, may be tidally stripped apart by the gravitational force of our galaxy, leaving behind, pristine stars in the halo of our galaxy. Besides, of course, halo stars which may have formed, as I said, when the galaxy itself formed. Stellar halo of all metal poor stars, most within about 30 kiloparsec, and stars could be debris from tidal disruption of dwarf galaxies. Now, in science, you may hypothesize, but ultimately you'll have to get observational evidence for it. Okay, and the observational evidence, for example, the tidal disruption comes from observations, for example, of a dwarf galaxy called Sagittarius dwarf. And while looking at the Sloan Digital Sky Survey stellar counts that by a citizen science project actually called Milky Way at Home, which studies the history of our galaxy by analyzing stars in the Milky Way's halo. This was Heidi Newberg's paper in 2002, termed a ghost of Sagittarius and lumps in the halo of the Milky Way. And they found concentrations of stars which could trace the trail. And this is actually a reconstruction of the orbit of the Sagittarius dwarf galaxy, and from which you can infer the existence of halo stars from tidal disruption of dwarf galaxies. Okay, and you may be able, this tidal disruption of gas or stars from galaxies is not confined to just the Sagittarius dwarf galaxy. When you map the the H1 gas in our galaxy, you'll find a lot of clouds which are actually moving about. And there is a stream of gas between the large Magellanic Cloud and the small Magellanic Cloud, which are interacting with one another. And some of this gas probably will get captured by our galaxy or is being captured by our galaxy as well, where gas is being stripped apart from one of these galaxies. And we shall see later that it appears to be from the small Magellanic Cloud. These two figures are actually flipped by 180 degrees. So this region is similar to this region over here, and the Magellanic Clouds which appear over here is appearing over here, and the plane of the galaxy is shown over here. So the evidence for tidal disruption of stars is actually not only in our galaxy, but in other galaxies as well, which I will just show you in a very short while. So I'll pause for a little while here. I'll finish maximum by 11:15 so that you get a bit of rest before the next class. Now I'll take a few questions. So Neil, you have a question?
Sir, why are the old stars metal poor and the newer one are metal rich?
Because the old ones would have formed from the pristine material, which should have been when the universe formed. The first elements which formed were in nucleosynthesis were hydrogen, helium, and the lighter elements like a little bit of lithium. Okay, so hydrogen, helium, lithium, bit of beryllium. Okay, the light elements formed, but the heavier elements could not have been formed in the early evolution of the universe. The heavier elements would have formed in the interiors of stars. So the new stars would have, so when the massive stars form, they die, they throw off the enriched material into the interstellar medium from which the new generation of stars are forming. So the new generation of stars will form from material which have been already enriched by earlier generations of stars. So the old pristine stars would have formed largely from hydrogen and helium. There may be a little bit of metal depending on when they formed, but that is why they are not metal rich. Whereas new stars will form from material which have been enriched with metals from earlier generations of stars, when the massive stars have exploded to enrich the interstellar medium with metals. Okay?
Okay, sir. Thank you.
Palak, you have a question?
Sir, what is the reason for existence of these arms?
Existence of these arms. I'll come to that in a short while. Lakshmi Raja?
Answer one more.
Yeah.
Sir, what is galaxy potential well?
Okay, any gravitational object will have a potential, right? For example, gravitational potential of the sun, of the earth, of any body, of the moon. Okay, so for example, when mass is concentrated, when mass is concentrated, gravity would decrease as 1 upon r squared, and accordingly the gravitational potential will also decrease with distance. So when I say potential well, I shouldn't probably use the word well over here, but basically the potential responding to the distribution of matter. Right? Well is more commonly used when it's a spherical distribution of matter, which can be taken as concentrated at one point. But basically, gravitational potential responding to the distribution of matter in our galaxy.
Okay.
Okay, so I will continue and then I will again pause in a little while.
Sir, I had a doubt.
Yeah.
Yeah, sir, how are we able to determine the boundary of a galaxy? Like, how are we able to determine that this is the end of our galaxy?
We will see that in a short while. Okay. I'll keep your question in mind. When I come to it, I will answer it. Okay.
Yes, sir.
Okay. Now, this is just a brief glimpse of our Milky Way at different wavelengths. Okay, and the top slide you can see over here is a radio continuum. There are no black holes, largely synchrotron emission. Okay, synchrotron emission, and which is non-terminal emission of highly relativistic particles gyrating in magnetic fields. Next one is neutral atomic hydrogen, which you're familiar with from Subhashish's lecture. And this is the spin-flip transition neutral atomic hydrogen. You can see that it has a small sort of scale height. Okay. Now, as we a small sort of scale height. One second, let me just sort of see. Okay. Then you'll also see the molecular hydrogen. Molecular hydrogen is called dense molecular clouds, which are in the plane of our galaxy. Then when you look at the infrared emission, infrared emission is long wavelength emission. So there again, you don't see the dark patches which you see in the optical images of the Milky Way, but the long wavelength emission is due to dust, and the shorter infrared emission is due to warmer dust plus low mass stars could be emitting, and optically you're familiar with. And X-rays is hot gas, and also there are X-ray binaries which accrete matter from a companion, gets heated up to very high temperatures and emit X-ray emission. Then we talked about, you've heard about supernova remnants, which also generate copious amounts of X-ray emission. Okay, due to hot gas, which is heated up to very high temperatures during the explosive phases of the universe, of a very high mass star. Okay, so you can see over here that across the waveband, across the different wavebands, what our galaxy looks like. Okay, and at very high energies, which is the gamma ray part of the electromagnetic spectrum, these are very high energy particles which emit gamma ray emission by a variety of processes ranging from both synchrotron as well as thermal emission, as well as generating secondary particles, hadronic processes as they're called. And supernova remnants can also emit in the gamma ray region of the electromagnetic spectrum. Gamma ray bursts are more sort of, I put over here, but this is not really our galaxy, but these are the most powerful gamma ray events in the universe in external galaxies. This is a blown up version of the radio image, which shows a 10G, which shows the synchrotron emission from our galaxy, disk of our galaxy, and you see spurs over here. This is called a North Polar spur, which is due to synchrotron emission and possibly a relatively nearby supernova remnant, which is projecting a large angle onto the plane of the sky. Now, to emit synchrotron emission, you need magnetic fields, right? And the magnetic field is another important component of our galaxy, because without magnetic fields, you would not be able to generate synchrotron emission. And this is, although the magnetic field has been known since the late 50s by the interstellar polarization of interstellar light, Hill and others have actually talked about it since the very early ages, that there were two classic papers by Hill and Hiltner in 1949, that this is a more recent image from the Planck satellite mission, and it's beautiful, giving the direction of the magnetic field in our galaxy. And typical magnetic field strength in our galaxy is about a few microgauss, and this emission, the interstellar polarization, is due to magnetic aligned asymmetric dust grains, which sort of absorbs light differently, the dichroic effect, which gives rise to polarization of interstellar light. But we can actually probe the magnetic fields also from radio observations. This is something which Desh and Prakash also sort of talked about, Desh particularly, about polarization of light, and give you very nice illustrations of the synchrotron radiation, rotation measure, Faraday drift, etc. So I'll just pick on that and show you that, from synchrotron theory too, you can infer the direction and the strength of the magnetic field without getting into details. Here I've shown you of a particular galaxy, NGC 6946, superposing the polarized intensity contours. These are the total intensity contours. These are polarized intensity. And these are tracers of young stars, which are regions of H alpha emission. That is, transitions to the Balmer series, H alpha, and transitions to n equal to 2. And you can see that the polarized emission is between the bars. So a lot of it is due to polarization, which has been emission, which has been depolarized. Harshini, I will take your question in just a minute, okay? In between the bars. So this radio observations also produce a way of looking at the polarization of the magnetic field of our galaxy, right? Now, here you can see that this is a rotation measure map. Okay? Rotation measure is something which Desh introduced to you very nicely, given excellent exposition of it, polarization of light, talked to you about rotation measure. And what you have over here are the rotation measures of about 37,000 sources, extragalactic sources seen through the plane of seen through our galaxy. And you can see that there are regions which are positive rotation measure, which are the red patches, and regions which are negative rotation measure, which are the blue patches over here. Positive are the ones where the field is towards the observer, and negative ones are the fields which are away from the observer. And from such observations, people try to reconstruct what the actual field structure might be. This one uses extragalactic sources, but you can also use pulsars, okay? But this is again a very unfolding story. This particular figure, which I took from a review by Rainer Beck, shows that only these two everybody agrees on. The others, the strength and the direction, people still sort of argue and debate about. So basically, we need to increase the number of sources, make better models based on that. And this one, more recent paper than the one which I showed you by Russ Taylor, Joren Still and others, Opperman, who you saw there was a hole in the earlier one. This one, the holes gets filled up, and you can also see that there are large regions of positive and negative, in addition to structures associated with probably individual features in our galaxy. So some argue that this may be a reflection of a large toroidal field. Some argue that this may be due to local effects, or it could be a combination of both. But these are again exciting areas in terms of trying to understand the magnetic fields of our galaxy by looking at Faraday rotation, which Desh described very nicely to us. Now, with the advent of the square kilometer array, I think one is going to see dramatic changes in this, because even in this, where you have more than 38,000, this has about 43,000 sources, I think, that we are still about only 1 degree, 1 source per square degree. So we need a finer grade to look at finer scale features and try and reconstruct what the magnetic field of our galaxy might look like. Okay, so I will pause again. There are a few hands up. Okay, Harshini, you had your hand up earlier. Go ahead.
Yes, sir. How do we map these magnetic fields and rotation measures, like for optical or for any other wavelength? We have telescopes, but how do we plot magnetic fields?
See, this was what, if you remember Desh's lecture, which is a very lucid illustration of polarization, that when you look at synchrotron radiation, the magnetic field is orthogonal to the direction of the E vector, provided you correct for the effects of rotation measure. Because when this electric vector travels through a magneto-ionic medium, it will be rotated, okay? It will be rotated, and by the way it rotates, how it varies with the square of the wavelength, you will find that you can determine the rotation measure. The rotation measure is proportional to the integral of the electron density multiplied by the parallel component of the magnetic field. So you can go and infer a direction of the magnetic field from the rotation measure. And from the synchrotron theory, you can go and estimate the sort of equipartition magnetic field or the strength of the magnetic field. So you can infer both direction as well as the strength from Faraday rotation and the basic physics of synchrotron theory, which I'm afraid I'll not be able to get into it, but we can talk offline if you want to know more about it. Okay?
Okay, understood, sir. Thanks.
Okay. Palak?
Sir, in the multiple wavelength image of the Milky Way, we saw that near the thin disk region, there were on both the sides, there were like 2 dense regions. So what were those?
Okay, actually the thing is that there are for example, in the disk of our galaxy also, there are regions which are more dense, which could be more dense to the other. For example, even in the rotation measure map, you saw that there were clumps in the Milky Way, in the plane of the galaxy. For example, there is a nebulous region called the Gum Nebula, Then there is also the Cygnus region, where there is a region of intense star formation, a lot of dense gas. So you should always remember that you're seeing things in projection, okay? And you also see that if you go towards the edge, even in this map, you can see there is a bit of sort of flaring up as well, okay? So it depends basically on the structure of the disk and the different constituents which make up the disk of the galaxy. Some of it which is actually closer, because here you're projecting everything onto the plane of the galaxy, that they will stand out much more prominently than the others. Okay.
Okay, sir.
Now, what I've shown over here is neutral hydrogen, and let me see how much time I have so that I know. Okay, it's 11. We'll close by 11:15 or 11:20 at the most. I've just shown you neutral atomic hydrogen over here and carbon monoxide over here. And you can see the dense gas, the dense carbon monoxide gas has a much thinner layer than the neutral atomic hydrogen, which is all I wanted to show you, because this is where, as I kept mentioning, is where the stellar nurseries are. This is when new stars are born, from the dense molecular clouds, which are cold and which are dense and which can collapse under gravity to form the new generations of stars. Whereas when you take neutral hydrogen, you've learned quite a bit from Subhashis about it, but there are different components of hydrogen as well at different temperatures. They have a larger scale height, could be a couple of kiloparsec or so, whereas depending upon the temperatures, etc. But over here, it will be much less than that, probably a couple of hundred parsecs or of that order. This one I have just illustrated to you the main components of the interstellar medium. The molecular clouds have the lowest temperatures, highest densities, largest fraction by mass. And as you go to warmer components, the densities decrease, fraction of mass for the diffuse clouds, which are cold but not too cold, not as cold as the molecular clouds, 40% by mass, slightly larger by volume. And the intercloud medium, which fills up a lot of volume, fraction of mass goes down, densities go down, temperatures go up. Coronal gas, which is the hot gas which I mentioned about, which you can see in the X-rays as well as from highly ionized species, fills up a lot of volume, very low mass, very low number density. These are per meter cube. So you divide by 10 to the power of 6 to get it into per centimeter cube, and very high temperatures of million degrees Kelvin. So my friend Sri Anand is going to talk to you in more detail, so I'm not going to spend much time on this over here. Now, we mentioned about the orbits of these stars. So if I look at the disk stars, okay, disk stars, they're moving about the center of the galaxy, all right? They're moving about the center of the galaxy, slightly wavy patterns as well, and that's what Gaia also tells us, okay, that it could not be absolutely in a plane, and the disk is also slightly warped. So they have stars in our immediate neighborhood, they are moving about randomly with small velocities, tens of kilometers per second. Of course, if we put it in kilometers per hour, it's a pretty large number, but we are moving around the galaxy at about 220 kilometers per second. This is what a differentially rotating galaxy is, and a rotating galaxy. But this is about a material in the disk. When you look at the bulge, they are actually moving about in random orbits. And also in the halo objects, they're moving about in random orbits. So stars in the bulge has been shown in red, halo with turquoise blue or green as they call it over here, whereas the one on the disk of the galaxy is rotating in the plane of the galaxy around the sun. Now we know that when things rotate about the central object, they would go down in velocity as in the solar system. Just applications of Kepler's laws of motion. Given the distribution of matter in our galaxy, this is what you would have expected to happen, right? This is the bulge light is modeled over here. The disk light is modeled over here. Using an equivalent of the mass inferred from the light which you see, you can go and calculate what the expected velocity variation. What you observe is nearly flat. And that is what gives rise to what we call dark matter. So this is actual measurements of the rotation curve of our galaxy, okay? And Subhashis talked about it, so I will not spend too much time on how it is measured, but this is the velocity at different distances from the center of our galaxy. There are wiggles along the way, but you can see it doesn't fall down like Kepler's, but particularly at large distances, it is nearly flat, right? And that is what leads to the existence of dark matter, as we shall see in a very short while. This is just repeating what Subhashish sort of told you. So I will go through it rather rapidly. We have a differentially rotating disk because V is nearly a constant, V is equal to R omega. So you'll find that the angular velocity would be larger when R is smaller compared to when it is further away. And he told you about how the velocity would vary with distance from us and how we can infer the rotation of our galaxy from that. And these are the angular velocities at distance R, and this is at our sun, so that when we are talking about objects which are moving in the same distance from the sun, this will be 0. And because it is differentially rotating, when R is small, this will be positive, whereas objects outside this, it will be negative. So we can, and it will have the maximum value when it is tangential to it over here, as we shall see in just a minute. I'm going to read rather rapidly because we've already done this. So at the closest point, it'll have the largest velocities here. At 1 and 3, which is within the solar circle, it will still be moving away from you from that equation which you wrote down over here. When you're on the circle or nearabouts, you'll get 0 velocity. If it is further away, you'll get negative velocity. So this is one way of trying to reconstruct the plane of the distribution of matter in our galaxy. Because where there is more hydrogen, you will also get a larger intensity. From the velocity, you can try and model a map of it. But the thing is that to get accurate distances, the gold standard is astrometry, which Gaia is doing, but there are all kinds of secondary calibrators from which you can estimate distances. Vishal and Balchan talked to you about how the electron density is used to measure pulsar distances from the dispersion measure. But if you had accurate distances to the objects, then you could also reverse the problem and look at how the electron density distribution is. So these are all processes which go towards getting a deeper understanding of our galaxy. Now, just to look at the existence of dark matter, we will look at just very simple basic physics which you know of, balancing centrifugal and gravity. If I have material which has a constant density, okay, constant density, then the mass within a radius r is 4 times pi r cubed, rho doesn't vary on density. If I substitute over here, this is what I'm going to get. And I'll find a relation that VR is proportional to the radius. So it increases. If it increases, then this is fine for the inner region of our galaxy, where V is proportional to R, just like a solid body, V is equal to R omega, where omega is a constant and V will keep increasing with radius. So a constant density with mass increasing with radius provides a good explanation for the central region, but it will not do for the outer region because the velocity is flat. So suppose I take a profile like this, rho R with rho 0 central values, r to the power of minus alpha, alpha is an index, and I can go and substitute back over here and I will get an expression VR is proportional to r to the power of 1 minus alpha by 2. So this is rooted in something called a singular isothermal sphere, which I'll not get into, but you can see straight away over here that if I had alpha equal to 2, I'll get 2 by 2 equal to 1, 1 minus 1 equal to 0, r to the power of 0 is 1. So VR is a constant. The rest of the constant of proportionality is just G, etc. All right, 4 pi, all that. So with a distribution like this, I can get a constant velocity. Okay. Now, but the problem with this is that, you know, mr is proportional to 4 times pi r cubed rho r. So if you put that over here, put r equal to 2, your mr will increase with r. So it clearly cannot keep increasing indefinitely. So we'll have to put a boundary somewhere. Comes back to the question of where is the outer boundary of the galaxy. Okay, we'll come back to it in a little while. And this is also not rooted in any other cosmological simulations. So ultimately, the way we see structures have to be rooted in the way we understand the structures evolved from the tiny fluctuations in the cosmic microwave background radiation. So one of the profiles is what is called the NFW, Navarro-Frank-White profile, which is something which has come up from simulations of dark matter from n-body simulations, studies of halos which form from the tiny initial density fluctuations. But we'll not get into too much of detail, but what we know now is that we are embedded in a dark matter. But from the motion of our object from our sun at a distance of 8 kiloparsec, applying Kepler's laws, you can go and estimate what is the mass within it. This is about a factor of 2 larger than the total mass in stars and gas which we estimate, and that is because, again, of dark matter. All right. So dark matter is not very high at the center. It keeps going up. We know it's not very high at the center because if it was equal density all along, the dynamics of material in the center would have been very different. It has to go up as we go from the center. So, so this is just reiterating that gravity from visible matter not sufficient to account for the observed rotation speeds. You need dark matter. So this is the image of our galaxy today, that we have luminous matter, okay, and luminous matter will keep decreasing with density till it becomes part of the general intergalactic medium. All right. So when you want to define the size of a galaxy, which is what one of the questions which is asked, which I wanted to come to it later, one usually defines it to a certain magnitude, sort of brightness limit. 26.5 magnitude per arc second squared is what is used. Magnitude is a measure of brightness which originated from Hipparchus, ancient Greece, and is still used widely. And some people use 25 magnitudes per arc second squared, but ultimately it would merge into the general intergalactic medium. So where you want to put the boundary would depend upon to what brightness limit you can calculate or you can estimate. Usually the fainter you go, it's more difficult to measure. So there is a working limit which astronomers use. But you can see that there is dark matter which contains most of the matter, most of the mass. More than 80% of the mass is dark. This is not only true of our galaxy, but it's true of other galaxies as well, right? So all our galaxies are embedded in dark matter halos. Now, one of the questions which you asked was about the spiral arms. Somebody asked how the spiral arms form, and I was going to ask you to, I request you to wait for a little while. So I'll spend a few minutes just telling you a brief overview of how spiral arms may have formed. Now, when you think of a differentially rotating disk, the automatic thing, okay, it is rotating, so if material at a certain point will go and form a disk. And these arms, when we talk about it, it could be formed. A trailing arm is one whose outer tip points in the direction opposite to galactic rotation, okay, trailing. And if it goes in the same direction, it's called leading. But almost all spirals, in most cases, all cases, the spiral arms are trailing, okay. Now, let's see what could be the reason for it, okay. First ingredient, as you also learned from your H1 experiment talk, is differential rotation. So if differential rotation would mean that we know that V is a constant, this is rotating, angular velocity is larger. So with time, it'll go into a spiral. That's the naive thing. But that is not a correct explanation, because if you let that be and you know how old the galaxy is, it's going to be really tightly wound up. And that is not consistent with observations. Some of the loosely bound arms are just about 10 to 30 degrees, versus this will give you a degree or two. So this is not the right explanation, rotation itself. So what is believed is that these are density waves, which are created due to the potential in which the stars are moving. And so spiral arms are locations where the stellar orbits are such that stars are more densely packed. The gas is also compressed, and once stars are more densely packed, gravity will be more, they will attract more mass into it. And this is where the new stars are forming, because that is where the gas is also there. And arms rotate with a pattern speed, not the speed of the galaxy rotation. So it is much less than the speed of rotation of the galaxy. So you see a pattern. So the problems of having very tightly wound spiral arms is also alleviated. But again, these are questions which are open questions, which one needs to sort of understand better. But that is sort of the current understanding of it. And for example, if the orbits are sort of ellipses, which are slightly disturbed due to the potentials, then you can see that there is a slightly greater concentration over here than over here, leading to the creation of spiral arms. Regions of higher gravity, objects such as gas clouds get attracted to it. Gas clouds aggregate, collide, form generations of stars, and they don't travel very far from the spiral arm. But the spiral arms are also transient phenomena. They're not going to live ever for the rest of the galaxy. Of course, they live for millions of years. Current estimates from Gaia, with looking at the distributions of young stars in them, puts it at about 100 million years or so. So it's too long a time scale for human observations to be able to actually look at changes in spiral arms, but you can see it in different arms at different stages of the evolution. I'm approaching 11:15. So I will round off with a few things. I'll take 5 minutes more at the most so that you have time for questions. So I've tried to address the questions as I went along, but obviously there'll be time for more questions as well. I'll show you a few pictures of the center of our galaxy. This is a beautiful image made by the Milky Way telescope, a stunning image showing you not only regions of H2 regions, but also supernova remnants and all kinds of activity going on. And these are filaments. These are highly magnetized filaments. And we still don't have a very good understanding of how and why these magnetic filaments are formed. This is a radio image. The MeerKAT is a radio telescope, which will be part of the Square Kilometre Array being built in South Africa. And it is even in its early stages have contributed immensely to the science. These are maps of the center of our galaxy. And I mentioned about the magnetic filaments, but they're also very dense star clusters, these are Hubble images which have been picked up at the infrared wavelength, because as I mentioned, there's a lot of gas and dust towards the center. So you really need a longer wavelengths to see it. And these star clusters have been picked up by NICMOS, which is the near infrared camera at the Hubble Space Telescope. It is marked over here. So these contain very massive stars, young stars which have formed hundreds of solar masses or so. And then this is the radio image, but what you see is hot gas which is coming out. Hot gas about 700 light years escaping from our galaxy along the polar directions. And these are possibly due to intense star formation in the center of our galaxy. The arches and quintuplet cluster are just examples of it. Some of it you may not have picked up at all. And the hot gas which is generated tends to escape perpendicular to the, along the directions of steepest density gradient perpendicular to the disk of the galaxy. But that is not enough as well. When you even look at higher energies, at gamma ray energies, Fermi telescope discovered these bubbles of plasma. Fermi is a gamma ray telescope, so these are often referred to as Fermi bubbles. And these extend to about 25,000 light years above and below the plane. And gamma rays are extremely high energy rays, and these possibly arise due to cosmic rays when they interact with gas and dust. And the supermassive black hole, which resides at the center of the galaxy, has also probably an important role to play. Catherine Blundell talked to you about the jets which are generated by supermassive black holes. Tomorrow, Shomak is going to talk to you about supermassive black holes in all kinds of galaxies, including our own galaxy. But the thing is that when the jet power is low, there were models which suggested that emission may be in the form of bubbles rather than collimation of jets. Whether this picture is entirely correct, we do not know, because today we have also seen narrow collimated jets in very low luminosity sources as well, including galaxies which are called starburst galaxies. Applications of Kepler's laws were basically used to infer the motion, the mass of the supermassive black hole in the center of our galaxy. This is an animation of the stellar orbits in the central 0.5 arc-second. Images, as you can see, the years go by from 1995 to about 2020. And from the motions of these objects, the black hole mass has been estimated to be about 4 million solar masses. And especially important is SO2 over here, which has completed one complete solar orbit. Now, this is a beautiful example of applications of basic physics in estimating in the center, looking at the center of our galaxy. Andrea Ghez and Reinhard Genzel were the prime movers of trying to measure this. And you have to have cooler stars, you have to be able to see through to that region. So you need to make these observations in infrared. Motion is very small, so you need the most sort of advanced optics, adaptive optics, to be able to measure positions accurately and infer it. Fantastic science, fantastic technological feat, and rightly deserved a Nobel Prize for being able to do that. This one actually, I will just show you a little bit of it. This one basically shows you a three-dimensional animation of the same motion. Just beautiful how the motions of stars, 25,000 light years away, have been monitored to try and infer the existence of a supermassive black hole in the center of our galaxy. And Shomak will talk to you about how it is estimated in other galaxies as well, and how supermassive black hole masses may be related to the galaxies themselves. I'll just probably spend 2 minutes telling you about this, since I'll close at 11:20, and that we are not alone. Okay, we are not alone. The Milky Way galaxy is part of a group called a local group of galaxies. And the two prominent spirals are the Milky Way and the Andromeda, whom we have met earlier. There is a smaller galaxy called a triangulum, which we also saw. Then there's a small elliptical galaxy near Andromeda, M32. We have met the large and the small Magellanic Clouds. We have met the Sagittarius dwarf, but the bulk of the galaxies are dwarfs, okay, are dwarf galaxies. And these dwarf galaxies actually interact with the main companion galaxies and get tidally torn apart and stripped apart. And the history of our galaxy may have been due to tidal stripping of earlier dwarf galaxies as well. And we have detected evidence of it in the Sagittarius dwarf. These are just images, close-up images of some of the galaxies which I mentioned. This is the Magellanic Stream, which we met about earlier. And I mentioned that I will tell you later about how they study these objects. This is something which you will know a little bit more, a lot more from Sri Anand's talk, where from distant background quasars, you can look at the absorption lines through this material and see what are the kind of metals or elements which make up this besides neutral atomic hydrogen. And from that, they've been able to infer that it most likely comes from the small Magellanic Cloud rather than the large Magellanic Cloud. These are exciting, interesting pieces of work. And stripping about of tidal dwarfs is not just unique to our galaxy, it happens in all galaxies. This is just a very classic example of a splinter or knife-edge galaxy seen edge-on, where you can see the beautiful trails of gases, of stars and gas stars, which have been ripped apart from tidal interactions of a dwarf galaxy in this particular galaxies. This is just an animation of what things might look like when Andromeda hits us. But just to reiterate that we are part of a larger structure, that there are different clusters of which the local group is just a part. This is a Fornix cluster, Eridanus cluster. This is a Virgo cluster in which resides the galaxy M87, and all these as part of larger cosmic web. This is the SDSS plot, the Sloan Digital Sky Survey plot of galaxies out to a distance of 670 megaparsec, given by a redshift of 0.14. And each dot is a galaxy over here. And what you see over here is that these are structures which form in the distribution of galaxies. But these are all embedded in dark matter halos, just like our own galaxy is. And one has been able to successfully reproduce this by following the growth of structures from the tiny fluctuations which one sees in a cosmic microwave background radiation. So we are a little part of this huge universe. So I will end over here and take a few questions. So hopefully the questions which are in between, I've answered during the course of covering the latter part.
Sure.
Sir, have we absorbed any galaxy in which the dark matter is not prominent?
Actually, the thing is that in any galaxy in which the dark matter is not prominent, the thing is that in almost all galaxies which have been studied, there is evidence of dark matter. There are galaxies which are very diffuse, low brightness surface galaxies. I'm not sure the dark matter has been actually established over there, but I can look it up and let you know later. But generally in galaxies, and in fact, Jairam Chengalur is going to talk to you about H1 neutral hydrogen galaxies. He has made extensive studies of what are called these dwarf galaxies, which I mentioned, which are small galaxies. And they've got a lot of interesting results. And they too, these dwarf galaxies also have dark matter in them. So the thing is that in very faint galaxies, we have not been able to establish it, but in galaxies we have generally studied, they're all embedded in dark matter.
And sir, do dwarf galaxies also have a black hole?
Dwarf galaxies, where they've been inferred, it's more of a challenge to infer it. You'll learn a bit more from this thing, but there are examples of dwarf galaxies with black holes.
Okay, sir.
So, in the halos of the galaxy, there are some older stars which you had said might be stars which are formed earlier in the same galaxy. So, could they be stars which migrated from the disk? They had formed in the disk earlier, and then they migrated.
I mean, at very great heights, probably unlikely, but to a certain distance, I think yes, it could be. Okay. For example, some of the pulsars which one sees above the disk of the galaxy, it could have got a kick which could have traveled upwards. But some amount of migration could be there. But most of the things which are far away from the disk of the galaxy, they're likely to be more pristine or tidally stripped from galaxies or small galaxies which may have merged.
Also, sir, The star formation in the galaxy mostly takes place in the disk, right?
Star formation mostly takes place in new star formation takes place in the disk of the galaxy. But if you think of the galaxy, of the formation of the galaxy itself, that the galaxy would have initially formed from the collapse of a cloud of gas. The clouds, while collapsing to form the galaxy, would have fragmented into various bits. So there could have been halo stars which have formed during the formation of the galaxy itself. And because they would have formed very early on in the evolution of the galaxy, their metal content would have been very low, very, very low. Whereas new stars which are forming in the disk of the galaxy, their metal content would be high because they formed from the later generations of stars. So that is the difference. But you're correct that if you look at the present star formation, it is in the disk of the galaxy.
Thank you.
Sir, when we like escape the Earth, then there is something like escape velocity. So, sir, is there something similar, like if we try to escape the galaxy also?
Okay, I didn't talk about that today, but the thing is that for example, suppose there are two things actually. Okay, one is the kind of objects which Catherine talked about, right? Catherine talked about which are radio jets. Catherine Blundell on radio galaxies and quasars. They could entrain material from the interstellar medium of the host galaxy and carry it along with it to hundreds of kiloparsecs away, isn't it?
Yes.
So there you're carrying interstellar material from the galaxy to the external medium. Okay, and you can find you also find evidence of that in clusters of galaxies, for example. That is one way in which you could carry material away from the galaxy. The other aspect is that our galaxy is, although I showed you a lot of activity, in terms of the range of scale of energies in galaxies, it is still, small. It's a little small. There are galaxies like the active galactic nuclei, which Catherine talked about, but also another category of galaxies called starburst galaxies, where the rate of star formation in the galaxy, which cannot be sustained through its entire life, but for brief periods could be even 1,000 to many thousand times larger than the size of our galaxy. So there'll be a lot of massive stars which will explode. And when they explode, they will heat up the medium, and these things will actually go up as fountains, just like the Fermi bubble which you see. So actually, Desh reminded me of talking about this recycling of material in the interstellar medium. But some of this material may also escape the gravitational potential of the galaxy, some of it. It is not clear how much, but one of the radio images I showed the halo of the galaxy, the magnetic field. But the halo consists of all kinds of components of the interstellar medium, from the dust to hot gas. So some of it may actually escape, some of it will fall down to the disk of the galaxy.
Okay, sir.
So we should probably stop,